This is our project for Intro to Computational Design and Analysis. We decided to optimize a MacBook laptop screen. So just a little introduction. Students often throw their laptops into their backpacks, which can unfortunately lead to the screen being cracked and damaged, which can cost a lot of money to that student because a lot of laptop users just simply toss their laptops into their bag. We need to optimize the material or even the dimensions of the screen to prevent further damage to that laptop. Most students use their laptops for everything from school and their work, so they are really important that they are always usable. The dimensions of the laptop that we chose, just a MacBook, the length is 14.09 inches, the width is 9.68 inches. Screen thickness, the original thickness is 0.1875 inches. The material is aluminum alloy. The density is 2,700 kilograms per meters cubed. The Poisson ratio is 0.33. The Young's modulus is 9,993,100 psi. The load, we just kind of estimated that it would be most students have 3 classes per day, and then the average weight of the textbook, so 3 classes times about 3 pounds is going to be either 9 to 9.5 pounds. And then the pressure is 0.0689 psi. And then each boundary condition is going to be an encaster on each corner of the screen. Here's just an image of the CAD model that we did for the laptop. We will just be optimizing the screen, so just the top part of the laptop. For the design optimization, we're going to change the material. Instead of aluminum, we're going to change it to titanium. The density of titanium is 4,420 kilograms per meters cubed. The Young's modulus is 120 gigapascals. The yield strength is 880 megapascals, and then the Poisson ratio is 0.35. And then another optimization is going to be to make the screen thicker, which will allow for less deflection when the load is applied. And then we added a 5% thickness from the original.
2 design variables in terms of materials. We used titanium on the left and aluminum 6061 on the right. The same force was applied to both materials of 0.0689 psi, and the magnitude of the displacement is shown in the contour plot. On the left, for the titanium, the magnitude was 2.204 times 10 to the negative 4th inches, and on the right, it was 3.885 times 10 to the negative 4th inches. Clearly, there's a difference. The aluminum displacement is almost twice as much as the titanium displacement, so the titanium is a stronger material and is resisting the displacement. On the next slide, we tested the thickness with just aluminum 6061. On the left, we have the same load of 0.0689 psi, but the thickness was increased by 5%, and this new thickness was 0.196875 inches. On the right, the test was done with 0.08 psi as the load and 0.2 inches as the thickness. The magnitude for the aluminum 6061 on the left was 3.239 times 10 to the negative 4th inches. That was the displacement in the middle, the maximum displacement. And the maximum displacement for the other aluminum was 3.616 times 10 to the negative 4th. So obviously there was a bigger load applied on the screen shown on the right of 0.08 psi. So this does have to do with the bigger displacement. But the thickness is not changing the displacement too much. I think it's mainly due to the psi. If we go to the next slide, the benefits of this change of the material and the thickness has to do with stronger material, and this ties into more of an economic cost. It's like a cost-benefit analysis. And if you look at it that way, the cost for a Mac might increase because of the different material, but at the same time, the risk of it breaking, the damage it could incur is reduced. So this would be a trade-off, but the trade-off is worth it, and there would be less damage. You would not have to worry about your Mac falling on the floor. You don't have to worry about your laptop going in your bag and bumping around with things. And this is very important because, especially for us students and people who use portable laptops like the MacBooks Pro, the MacBook Air, it's very important to ensure that it's safe at all times. And if the material change happens, then it would be safe and we wouldn't have to worry about as much damage that could happen if we drop it. On the next screen, we see the analysis methodology, and we entered Young's modulus and Poisson's ratio for both material properties of aluminum 6061, which is shown here, and titanium. For aluminum 6061, the Young's modulus was 9993100, and Poisson's ratio was 0.33. When we did the boundary conditions for this analysis, we encastered the outer edge, so all the rounded edges and the side edges. And the force we used was a uniform pressure over the top surface. We decided not to do a point load because that's not the most accurate depiction of what would happen. Most likely, if any screen or laptop fell, it would fall uniformly or even on one edge or something like that. A point load could be done, but we decided we used a uniform pressure because we want to show that force analysis. When we did the TET mesh, we had to use the TET mesh because the other mesh methods did not work, and all these are shown on the next screen. So here on the top left, we see the uniform surface pressure. On the top right, we see the encastered edges, and at the bottom, we see the TET mesh we used to run the job.
Hello, I will talk about the optimized design and the optimization results. So first, we were optimizing thickness and Young's modulus. So our optimal values for that were 0.25 inches and 1.73 e to the 7 psi. Here on the right, you can see the constraints. So we limited our thickness to be between 0.1 to 0.25 inches, and we limited our Young's modulus to be between 0.9 and 1.74 e to the 7 psi. Here on the left, you can see the final value for our deflection. This aligned with our abacus results very well, and you can see the exit flag value of 1 proving feasibility. On the next slide, you'll see the Taylor series function that we used in order to find the optimal x1 and x2 values, and below that you can see the spreadsheet that we used in order to derive our linear approximation. So here you can see the thickness, and then you can see the load, which we didn't use, and then you can see the modulus, the original values for that, and then we did a delta of 5% in order to get to our linear approximation. And then here on the right, you can see the comparison with the FEM results using a test point of 0.2 and 1.05 e to the 7. In abacus, titanium overall was an improvement in comparison to aluminum in minimizing the deflection, and sticking with aluminum but simply increasing the thickness by 5% also proved to be an improvement in minimizing our deflection. With MATLAB, it resulted that the best results in order to minimize our deflection were at the upper bounds, so 0.25 and the upper Young's modulus as mentioned previously. So to conclude, again, titanium overall better than aluminum in order to minimize the deflection while maintaining the same thickness. With our one-dimensional Taylor series function, the upper bounds proved to be the better parameters. In adding to that, we should further analyze weight versus deflection and try to minimize that. We should also look into our constraints and not just limiting ourselves with aluminum and titanium. And we should also look at the minimum and maximum thicknesses and how we chose those constraints. And in order to conclude this, we wanted to just say that we recommend to design the laptop screen, obviously within the constraints, but at the upper bounds in terms of thickness, and at the upper bounds in terms of Young's modulus.